Is it going? Yep. Okay. So last time we were creating some streams, right? We created our own input and our own output stream, and if you remember last time, we created this this output stream called alphabet, which can be read from. So readable streams are output streams. This guy just goes through the entire alphabet one character at a time. This is the model for doing object-oriented stuff in JavaScript. And then the read function, which we overwrite, that came from Readable. Readables has nothing in it. We have something that now has something in it. It just goes through every letter of the alphabet and spits it out until we finally cut the stream off. Okay? So I think if you remember, we ran this last time, and all it does is it spits the letters of the alphabet to the screen, no harm, no foul. Then we wrote our own writable stream. Okay, so something out. So this would be an input stream, something we can write to. All right, this guy again. Here's the model for object-oriented stuff in JavaScript. This guy inherits from stream writable. We've overridden the write function for this guy, and all we do is we keep concatenating it onto a buffer over and over and over again. And in the end, when all is said and done, when it's finished, we store the value we just read inside this buffer with our key. So the key is here, the value is here. It started off as null. What did it become? It became this buffer. Make sense? Okay, so it became a buffer with this new value concatenated onto it over and over and over again. All right, so this is where we give value to the value. Started off as null, and this is where we actually finally, in the final last event, write it here. All right, and this kind of comes down to this idea of asynchronous events. So we talked a little bit about this right at the end of class last time, but what we have is we have all of these scenarios that are going on. So typically on a web server, this server, so here we'll just say this is our server. Doesn't have to be a web server, it could be any kind of server. So this server is handling all sorts of requests, things like that, and behind the scenes, the traditional model says we're going to spawn off, here let's just call them all T's. We're going to spawn off threads for all this stuff. Okay, so we're going to have threads floating all over the place. Ooh. To do different tasks. All right, so even in this little model where we just have 3 threads, which doesn't seem like it's that big a deal, each of these threads is utilizing system resources on the server. Well, what's a server? A server has several things associated with it. It has RAM. Well, here, let's actually just do it with text here. So we have RAM, we have hard drive, we have CPU. Let's just call those the resources that we really care about. All right, so this machine has a single bank of RAM, potentially multiple hard drives, but in our simple sense, we can just think about this as being some memory. Maybe this is 4 or 8 gigabytes of memory, a single hard drive, and a dual, we can even say quad-core CPU, doesn't matter. A decent CPU. Now, in our little scenario here, when this guy spawns off multiple threads, remember threads are lightweight processes. So they're actually owned by a top-level process. Let me send this to the back. Okay, so all of these threads are getting portions of this process's CPU time. So this process is getting some CPU time, and maybe this guy is, let's just say he's the authentication handler or something like that for this server. Giving us an example of a single program running on the server that's doing something, spawning off multiple threads. So let's say that this process in this little world gets, I don't know, let's just say it gets 100 cycles on the CPU. So it gets to issue 100 commands on the CPU before it has to relinquish the CPU to some other aspect of the operating system. Okay? So as this guy's going through, this process now has to manage his internal threads. So right off the bat, let's just say out of these 100 cycles, let's go ahead and cut 20 of them off. Now we have 80 cycles left over. So we're going to say that we have 20 cycles. 20% of its time is going to be spent managing threads now, not doing anything productive. Okay? He's got a workforce to work on. All right, now for each of these guys, let's say he's going to give each of these guys 20 cycles. Okay, so this guy gets 20, 20, 20, so that's 60 cycles left over. Oh, 60 cycles, so now we're down to 20 cycles total. These last 20 cycles are going to be for transitioning between threads. Make sense? So our 100 cycles that were allocated to us turns into something kind of like 60 cycles of actual productivity when you have 3 threads. And obviously, as you get more threads, the efficiency of your productivity is going to continue to decrease, right? All right. Now, certain things from multiple core CPUs that might increase as well. That might help keep it from falling so quickly. But the more threads you have, the more less efficient your efficiency is going to be. The less optimized your efficiency is going to be. It's fair enough. Now, that's just for doing number crunching. That's the best case scenario for us. Worst case scenario for us is I/O. We talked about this a little bit at the end of last class where I mentioned, if you've ever written a program that just prints a bunch of crap to the screen, well, that program is going to take a long time if it writes a bunch of crap to the screen. I think we have done math where we've added up 1,000,000 numbers and it happens almost instantly. You print out 1,000,000 things, it doesn't happen so instantly. Okay. I/O is really, really, really expensive. So now, I/O in this case is anytime where, let's just talk about the worst case I/O, is anytime we're reading and writing to the hard drive. It's also I/O whenever we're reading and writing from RAM. It's also I/O when we're reading or writing to reading from the keyboard, writing to the screen. That's all I/O. And actually, that's even worse I/O, especially reading from the keyboard, because we are at the mercy of how fast the user types stuff in. Make sense? Okay, so I/O is the enemy. So we can write that here. I/O is the enemy. So does that mean we just decide we're never going to do input-output in our programs? Yep. Just get rid of that? Is that an option?
Don't need it.
Solving problems in real life, could we get by without I/O? If you couldn't ask anybody questions to receive the input, if you couldn't say anything to other people, tell them things, could we get anything done? If all we can do is just think internally in our head, we're autonomous, but with zero communication, zero connectivity with anything else in our environment. If we can't even pick up the computer or pick up a soda or pick up our hat, couldn't do any of that. So we can't interact with it.
Meditating the whole time.
Problem solving efficiency goes way, 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 way down to nothing, right? Okay, so I/O is the enemy, but it's necessary. We need to have I/O. So a goal of Node is to maximize the efficiency of I/O. Or we might say minimize the impact that I/O has on the efficiency of our program. So the way this works is with Node, we have our server. The server is a process. So this is a program running on the computer. And this guy has exactly one master thread running on the server. Okay? This guy handles everything that is non-I/O. Number crunching crap. And number crunching crap is fast. Okay? Just like we looked at the example, we print out 1,000,000 numbers, takes forever. Add 1,000,000 numbers, Happens almost instantly. Computers are really good at number crunching. Less efficient when it comes to I/O stuff. So, having said that, we're going to have a single master thread, and this guy handles all number crunching. All right, so this guy's handling all number crunching. Now, we still have to handle I/O. It's the enemy, but we still have to handle it. So what they do is they use what's called an asynchronous model for I/O. So down here, we're going to have, these are the I/O things. So let's just call this, this is an I/O factory.
Put little smokestacks on it.
So this I/O factory handles all I/O things. All right. On top of this, we have something called the node event loop. So there's your smokestack. All right, so that's the node event loop. The node event loop constantly works through requests, specifically I/O requests. So we might have a big stack of these requests. And it's going to be, for simplicity's sake, we're going to say first come, first serve. These guys get in line. And the event loop just keeps spinning through, spinning through, spinning through, taking whoever's next in line, performing the task that they need, deleting them from the queue. Done. Handling the next guy in line, deleting them from the queue. Done. So on and so forth. Okay? This guy over here represents asynchronous communication. Okay, and it's asynchronous because we are not stalling our entire thing up here. We're not blocking. So in other programs that we've written, either in other classes or as well as our server we wrote in here, if we do something that blocks, we have this line of code, this line of code, this line of code, and say this guy blocks, we don't get to the next line of code until the blocking line of code is complete. And this guy might go and he might be waiting for a user to enter their password, let's say. Now, in most cases, if you're waiting on a user to enter a password, the next line is going to probably be authenticating. So you probably want that next line to wait till the password's been entered in. Okay? But that's still an efficiency problem because this guy is keeping us from doing any work whatsoever. Okay? There's a whole bunch of work that could be getting done, not related to the data we're waiting on. But we're not doing any work right now except just waiting on the human. So the CPU, this guy, is sitting here doing nothing. So we want to minimize blocking in Node. So we have all the number crunching stuff happening all the time. This is just happening continuously because nothing up here blocks. That's the goal of Node, is never, ever block. And we accomplish this by saying anything that typically would block, which is I/O stuff, we're going to toss towards the I/O factory. So rather than block it, we're going to have it and we're going to deal with it by throwing it at the factory. Historically, the way we would handle this is we'd spawn off a thread. Here's an I/O request, here's a thread. Here's another I/O request, here's the thread, if we didn't want them to block. Well, we just looked at a model where having multiple threads really hurts efficiency. Threads are expensive. The process that owns a thread has to micromanage them. It has, it's in charge of a zillion threads running at once. Even just creating a thread and starting the thread running is expensive. It uses up a lot of CPU resources, uses a lot of time. Nothing is happening efficiency, but we're not blocking. Okay, so that's the punchline is that threads do allow us to get past the blocking problem with a cost. Threads are still better than processes. Well, maybe not from a a speed perspective, but certainly from a good stewardship of using the system resources perspective. Multiple processes just says we're going to, oh, you need to do more than one thing at once. We'll just get another program running, and we'll let the CPU now give you twice as much CPU time as you used to get, instead of sharing all your CPU time among one process, sharing amongst all the threads. But in any case, the punchline for us in here, because those are more operating system discussions, the punchline for us in here, threads are expensive. They solve the blocking problem, but by modern standards, not very well. Or we could say by nodes standards, not very well. And we're going to just pigeonhole and say all the stuff that blocks falls into this category of I/O stuff. So anytime that we would have something that blocks, we're going to throw it at the monster down here called I/O factory rather than spawn off threads to deal with each one. Okay? So realistically, this guy's probably running in his own thread because this guy's not blocking, right? So really, if we're really modeling this, we'd throw a second thread down here. So this guy is really, that I/O factory is really running in his own little thread. But we have two threads, main thread and the I/O factory thread, handling everything. Two threads, not a big deal, especially since when we started the server, we probably spawned off those two threads. So now we don't have the overhead of having to create those threads on the fly. They were already there, they were already running. And we're never going to kill off the threads because this guy's never done. The event loop just keeps running in perpetuity. If he has nothing to do here, he just keeps spinning and keeps checking. That's all this thread is doing. And is he using up CPU time? Sure, he's using up CPU time, but he's only sharing CPU time with one additional thread. Pretty efficient, especially when you consider that modern day computers, even the budget pleaser computer, does it probably have at least 2 cores in it? You can get a Core i5 computer. They make quad-core Core i5s as well, but you can't buy a single-core CPU anymore. They don't exist.
They still sell Celerons.
They don't sell Celeron.
People buy them.
From who?
Best Buy sells them.
Best Buy has Celerons on the shelf.
Yes. Toshiba's still putting Celerons in laptops. Not kidding. It's a horrible.
No, that's not possible.
Yes.
Are these like the netbooks?
No, they're the budget pleaser computers. They're like $240. It's a horrible.
Dual-core Celerons, though?
Well, I mean, they don't make Celerons anymore. It would be a Core i3 would be the cheapo.
They still put Pentiums in them too.
Bring something up and show that to me. I don't believe that.
Let me find it.
All right. So in any case,
There it is.
within reason, let me see.
$229.99. Sold out of them too. Horrible computer.
N2840. Let's see what that is.
I was ready to call one customer an
The
idiot.
N2830 is dual-core, so the 2840 has to be dual-core.
Well, right, but I want to know N28.
Two cores.
Well, regardless, I mean, that's fine. I didn't know they still made Celeron processors. This isn't even, I mean, that's an architecture that's 15 years old.
I know.
Longer? No, that's older than that.
And people buy them. I told
Celerons
them.
were out in 1998.
I tell people.
Did they just bring this back and
No.
start calling them Celerons?
No.
This can't be the same processor.
See, if you understand that, why do you let them buy it?
See, this is
Don't.
launched in 2013.
2006.
Where was the 6? I saw 9.
Yeah,
Like $465. Did they relaunch the Celeron?
Yeah, it looks like they did.
Okay.
I see an 09. See, 08.
06.
06.
Yeah, it's pretty old. So really, we had an 06, and then there was 2 models in 08, and there was an 09. I think I saw down here, but it really looks like they may be. Well, here's some 11s, some 12s.
Interactive support.
Well, regardless, still a two-core processor, right? So, in a worst case, even if we buy a budget pleaser computer, you're going to have 1 core to handle this thread and another core to handle this thread. You're reliant on the operating system to make sure the threads get as much CPU time as possible. Let's say they're going to get at least 90% of what they should. Fair enough. All right, so you're getting pretty maximum of efficiency out of this. The only caveat, though, is that when we're working with I/O stuff, we have to assume they're happening in a certain order. Okay, because this guy's going to handle them first come, first serve, and events are going to get raised, asynchronous events. And what happens then is each of these becomes an event that gets tossed onto an event stack, event queue, depending on whether you think this guy's feeding off the top or feeding off the front of the line, depending how you want to visualize it. But in any case, it's first come, first serve, which would be a queue. And the I/O factory will deal with the next event. So looking at our code here as an example, when this write stream, when it finishes, when it finally finishes, it's going to call the callback. It's going to go multiple times, multiple times, multiple times. When this guy finally no longer has anything to write, what's ultimately going to happen? The finish event will get pushed onto, or will get in line with the I/O factory. That becomes an asynchronous event. It did not block. Okay, this happens separate from the rest of the processing. So while we're still over here doing other things, this guy got in line to eventually be processed by the I/O factory, which then will go and actually throw the stuff into this array, if you will. That makes sense? Okay, so this is how Node handles things. But because it handles things that way, we have to keep that in mind when we write the rest of our code. Okay, we need to know when certain things happen, and we can asynchronously become aware of those things as well. So for instance, let's just say that over in your code over here, we are reliant on the value that ultimately gets pushed into the store variable of our cache. Okay, we're reliant on that. Well, as we're cooking along doing math, and we finish reading from this guy, and this guy asynchronously says, okay, I'm finished, go ahead and store me in the store. This guy can't go on and do that stuff until this has been completed, correct? Well, like I said a few minutes ago, the main rule, or a main rule in Node, it's maybe even fair to say the main rule in Node, is don't block. Well, at the same time, we could say, don't read this value till it's there, correct? So we can actually put another event in here where we actually use the value here as the result of an event over here, which this guy notifies us of. So now you have I/O events letting other I/O events know that they've been processed. Make sense? So as long as we put that second one onto as long as the second one got in line after the first one will definitely be processed first, which will then let the second one know that things are good. And at that time, actually, is when he would really get in line to get processed. Okay, so there might be a little bit of a delay anyways.
So the first guy does let the second one know. The second one can't just get in line and just assume that the first one is going to finish before he gets there?
Well, somebody has to raise the event. So things only get into the line here at the event loop if the event was raised. So if this event here is the done writing store event, Okay, and this guy, this event was done writing, done write stream. Let's just say that for that one. The done write stream will be in line first. And what does the done write stream do? In the end, he does this. So actually the name of this event was finish. So to use the correct terms here, we say finish. All right, that's the finished event. So the finish event will eventually get handled by the IO factory. And in that finish event, this guy we don't in this case, but we may raise another event that allows, maybe this guy's called the ready event. And the ready event gets raised, which allows this guy to know that he can now go and do what he needs to do. And this finished event has now completed. And at that point in time, when it raised that ready event, this guy gets in line. He might be next in line, he might be 300th in line. We don't know, but he's in line to get handled by the IO factory. All we do know for sure is that this guy has already left the IO factory before this guy is even notified, because he received an asynchronous event letting him know that this guy raised the ready event, which let this guy know, like, oh, it's good to go, I'm going to go get in line. Doors are open. Then whenever he gets to the front of the line, he'll get processed.
Where is he before he jumps in line?
Well, where's this guy before we do it? It's going to be associated with a constructor somewhere where an object registers itself to be a listener for an event. Okay, so this code right here is an untapped resource until somebody actually raises the finish event. Okay, it's just sitting there saying, okay, I'm going to kind of keep my eyes open, keep my ears open, listening for that the event finish. And as soon as that happens, then I'm going to react to it. And how am I going to react to it? Well, I'm going to get in line and wait till it's my turn to deal with the finish event.
Is that kind of like observers and Objective-C for the events being raised?
Well, sure, it's pretty similar to that. Yeah, where you have guys who are constantly, waiting for an event, but the important thing is these guys are not blocking. Okay, so if where are we at here? If this guy, the guy who had the ready thing, let's just say that this is our, let's say we have another object in here called, what would be a good name for an object? Let's call this guy read cache. So we have another object, and his job is to read the cache after it's been stored. So the cache's job is what we did is we piped the output of our input stream from alphabet into the output stream that is our write, which then ultimately stored it inside of a buffer, which then wrote it to our cache. This guy, this other object, his job now is to read from that cache. All right, so he knows that before he can actually utilize the cache, he needs to wait for a ready event to occur, which means inside of his code, he can do anything else he wants, but anything that involves using the store associated with the cache is going to have to be wrapped inside of a closure associated with an event. So, for instance, the example we used here is that it's the ready event. So as soon as this guy raises that ready event, which means that I have put the stuff into cache's store, you can now use that variable because there's something there. Then he becomes notified, which then asynchronously will call the closure associated with that event. Just like the finish event here got called automatically by who? He got called automatically by the callback here, which came with the write function. So the write function requires a chunk encoding and a callback function. That's what it needs to work. And here's the constructor for it. The constructor, we started him off as a base class of Writable. And Writable has that callback function for you, and the callback function is a function that raises an event called finish. Okay, so this dude got called for us. That guy got made for us. We didn't define it anywhere up here. It came with the constructor. That make sense? How that works? All right, so let's go this route then.
Professor,
Yep.
does the IO factory process each event at a time?
One event at a time.
For example, if there are two clients, one make a request to download a big file.
Yep.
And another client requests just a homepage.
Mm-hmm.
And this first guy requests, and
Does the second guy have to wait for a giant file to finish downloading before? It does process them one at a time, so it would be in your best interest when writing Node code, when writing asynchronous Node code, not to block. And reading a large file would be a blocking thing. That's going to prevent somebody else from continuing. So by nature, Node's going, in your example, if there's a 4 GB file that you're downloading, before the other guy is allowed to read a web page, read a single little tiny file, by your example, this would be a poor model. It would be a memory efficient model, but because you're too, so this is a large file. This is your large file event that it's dealing with, and then this is your small file event. We don't get to this guy until this guy's done. It's possible in some implementations of Node, if you put it into like enterprise mode, it might allow this guy to become multi-threaded. But you're going to have to control that because you don't want to get into the problem you're trying to solve. You have multiple threads that are taking up all these system resources. So there probably is a scenario where both of these guys could be simultaneously dealt with, because something like this is going to be dealt with very quickly. This might only take, in human time, some fraction of a second, where this guy in human time might take 10 minutes. Well, we don't want to have to wait 10 minutes for something that only takes a fraction of a second to complete. So we'd like for these two things to happen at the same time, but that comes with side effect. Like what we just said before, it's important that these guys happen in a certain order just in case this guy is reliant on this guy being done. But if that were the case, this guy would have not been added to the event loop yet, because this guy would not have raised the event that allowed him to add himself to the event loop. So with that in mind, would it ever make sense to have two threads here? Since things that are reliant on other things I think it would make more sense not to serve large files using Node. I think that would make more sense than multi-threading it. Okay.
Could there be like a conditional, a conditional in there that only spawns off the other thread if it encounters a large file?
Well, I suppose if you wanted to,
that way
you could situationally spawn a thread off in here. You could spawn a JavaScript thread off, but I think it would not be best practices. The point of Node, Node is essentially a structure that they're trying to get you to adhere to. And that structure indicates that you need to have, you need to not block, and you need to minimize your number of threads. So typically, if you start blocking for some reason, that's bad if you're doing a Node implementation. And if you are spawning off threads for any reason, probably doing it wrong if you're doing this the Node way. So this is really a new paradigm of thinking. Skip that. So here's this event loop we were just talking about. Yeah, there we go. I/O is slow, blocking I/O, threaded I/O, bad, bad, bad. So here's kind of an example of what that IO factory looks like for us. So while there's still events to process, get the next event. If there's a function associated with it, call the function. So process events. This code right here is the pseudocode version of this picture. Okay? And we've already seen this earlier when you remember we were dealing with the RESTful calls with this guy. We would have an event associated with /items, and this guy had a, an on-end event would get called, which had an enclosure. Here's a function, and this guy would get called. Make sense? So we'd have a get event. The get event would notice the path you gave it, and then we'd have an end event once the get is done that would get raised, and it would call this function. This guy's called a closure. Whenever we say closure, that's a function that's being passed as a parameter to another function. That's a closure. Okay, we already talked about this, the implications of the event loop. You must not block under any circumstances. Bad news bears. Okay? Node is a non-blocking type thing. Here's that callback pattern we've kind of already seen. So let me actually grab this, and we'll throw this into Sublime here. All right. So we're creating a variable called control panel, and this guy is going to be equal to a function. This is kind of a cool thing with a lot of these loosely typed languages, and something we're not used to from our general purpose languages like Java. Well, JavaScript's still a general purpose language, but I guess just loosely typed versus strongly typed languages. But in any case, functions are first-class, what are called first-class citizens in, functions are first-class objects in JavaScript. And those of you who are taking 470 next semester, you'll be dealing with that a lot because Scheme allows you to pass functions into other functions. So pretty much a common thing here. So this control panel, we're actually storing a function inside of a variable. And this guy has an initial thing just called OnClick callback, and it starts off as null. Here's our object. We have an OnClick part of the prototype. So we have a control panel prototype. We're adding an OnClick method to that. This guy is going to be a function that takes in a callback, and it's going to write to the console that it registered with that click callback. And then it's going to set this guy's OnClick callback equal to callback. So this field right here, we're starting to label these. This guy is a field associated with the control panel object. Okay. This guy is a method associated with it. And what does this method do? It sets the OnClick callback equal to whatever function was passed in here. Somebody's going to pass us an actual function as a parameter to this function. And we just write out that we've registered the callback. And what does that mean in this case? It just means that we set this variable equal to this callback function. So this is where we're storing a function inside of a variable. Okay. Then we have the click function associated with this object. And this guy is going to take in a button color. That is the color of the button that was clicked. Okay. And if we don't have an OnClick callback, that is, if this guy hasn't already been set, what does that mean? If we click a button, and this guy gets called, passing the button color red in, and we get inside of this if statement, what does that mean? What did we forget to do?
Change that field from null.
Okay, it's true, which means we forgot to do what?
Does that trigger the event or?
We didn't do this crap?
Yeah.
And what's this crap? This is registering the OnClick callback. We forgot to set the button up to be we forgot to set the control panel up to be aware of button clicks. We clicked the button before we told this guy to pay attention for us clicking the button. Make sense? That's asynchronous communication. We tell him to pay attention. That way, when we do click the button, he becomes aware of it. If OnClick callback is equal to null, that's what this says. If not this .onClick callback, that's saying if this .onClick callback is equal to null, that means this guy still has his default value, which means we never actually registered the callback with the control panel for that button to deal with the click event of the button. Okay? So, forgot to register the callback, just return because we can't do anything in response to the click. Why not? Well, if we start trying to call stuff on this function, we're going to have some problems. We're going to get those null pointer exceptions that we don't like. Okay? Otherwise, if we're still... Go ahead.
Love those things.
Which?
No pointer.
No pointer exceptions? Yeah, very fun. Okay, so if we're still kicking here, because remember we have a return statement, so return makes a function immediately end. Okay, so if we're still kicking here, we're still in the function, we're just asking a question. What color was the button? So if we're still here, that means we already have an OnClick event handler. That's our callback here. We would usually refer to that as a handler. Okay? So if the button is green, that is, if the button that called this guy let us know that his color is green, then what are we going to do? We're going to call OnClick callback, passing it the string all okay. Okay? So that must mean that whatever this guy holds, the function that this guy holds, takes what as a parameter? String. Or I've written bad code. Or whoever I copied this from wrote bad code. Okay? We're passing the OnClick callback a string, so we would expect that whoever passed this callback function in here set it equal to something that takes a string. Reasonable assumption, right? All right. So button was green, we're going to say all okay. Button was red, we're going to say panic, just like driving. Don't hit the gas when you got a red light. Bad news bears.
Hit it when you get the yellow.
That's right. Gun the gas.
Green means go, yellow means go faster, and red means slam on the brakes because you didn't go fast enough.
You can go fast enough in the yellow?
Yeah.
Okay. All right, so that's what this guy does. This actually handles a click event, and it handles it by calling the callback that we registered for the handler. All right? So then down here, this is when we actually create an instance of our control panel. Then we let our instance of our control panel know about what to do on OnClick. Right here is, we would say, this next line is where we register with the OnClick event. So control panel, OnClick, we're passing it. This guy takes in a callback. So callback is kind of a name for a function. Remember, we got this from a section called callback pattern. This is the callback pattern. And this is something that's common in most modern programming languages, where when some event occurs, we call back with a function that we said earlier. Okay? So kind of like when somebody calls you on your phone and you don't pick up, you get the voicemail. They're letting you know to call them back and perform some task. In real life, we kind of just do whatever the heck we want. But in this case, they've let me know exactly how I should respond when I get a chance. And who's going to be responding when they get a chance in this case? It's going to be the I/O factory. This dude. Okay? So, on click, we're going to pass it this function. What's this guy called, Abe? What I have highlighted there? I have highlighted from here to here. Right here, the beginning of the F in function, to right after this closing curly brace. What kind of animal is that? We referred to it several times today.
I know it. I know that we've referred to it several times. Thing that pass functions starts with a D or a D or some other.
Or a CL. Start with a CL.
Letters that's in between B and D.
Closure.
That.
Closure. All right, so this guy's a closure. So we're passing the OnClick function that we defined up here. We're passing this guy his parameter. His parameter is a callback, which is typical naming convention for a function. You could call this Bob if you wanted to, but callback is kind of our normal naming convention for give me a function that I'm going to use when I call back. So we'll pass it this function. What does this function take? It takes in a variable called status, which we've kind of already seen is probably a string. At least it uses it as if it's a string. And when we call OnClick on that, this guy takes in the status and he says received click callback, and then he reads out the status. Then we call click 2 times. Call it the first time, passing it the color of the first light, green. Second time, passing it the color of the second light, red. We register this callback with the OnClick listener, this guy. Then we call click, passing it green. We pass this test because we had already registered it here. When we call it on green, we notice button color is green. We say all okay. Otherwise, we say panic. So if I run this, what will the output of this program be?
All okay and then panic.
All okay, then panic. Okay, first time we call it with green, it's all okay. Second time we call it with red, it's panic. What if I don't do that line? What if I omit this guy right here? We're never registering with the callback. So if I don't do this line, if I don't pass the callback function in here, I don't see registered click callback, which you didn't tell me it outputs. I don't see click callback. I don't see, here's the call to it, this done on click callback, all okay. So this guy takes in a status. So actually what I'll see is, for the regular version of this, I'll see registered click callback, then I'll see received click callback, then I'll see all okay, then I'll see received click callback, then I'll see panic. That's all the stuff I'll see. Make sense? All right. I was going to give you homework, but we're over time, so I'll see everybody on Monday.